Concentration is defined as the quantity of a solute dissolved within a given quantity of either the solvent or the solution. Concentration can be expressed in a variety of units. One possible way that concentration can be expressed is grams per liter of solution. And when we talk about a solution that is less concentrated, what we really mean is that it just has less particles per unit volume compared to other solutions that are more concentrated, which have a lot more particles per unit volume. One of the more common ways that we express concentration is with molarity. Molarity is a unit of concentration that expresses the number of moles of solute dissolved per liter of solution, and that's a very important detail right there. Because when we express molarity, we're talking about liters of the entire mixture. The units of molarity are expressed as moles per liter, or sometimes that's just abbreviated as capital M or molar. You can see that there's three solutions here with different concentrations. This solution here has a 0.5 molar concentration, and that would be a fairly dilute solution. If we increase the molarity or multiply it by a factor of 3 to create a 1.5 molar solution, it's simply just going to have more particles of the solute per unit volume. And the higher the molarity gets, the more concentrated the solution is. The lower the molarity is, the more dilute that solution is. Molarity is expressed as a math equation. Capital M represents the concentration of the solution in moles per liter or molar. Lowercase n, just as with the ideal gas law, represents the number of moles, but that's the moles of solute only. And capital V in the denominator represents liters of solution, and that's a very important distinction here. Sometimes we use milliliters to count units of volume, but we need to make sure that that denominator is being expressed in actual liters. In this example, we have a solution that's made of 0.150 moles of sodium chloride, and we've prepared the solution to be 2 liters. In order to calculate the molarity, I know my number of moles and I know my volume. Now I can just simply substitute those values into the molarity equation, and my final molarity for this solution comes out to be 0.0750 molar. I can either express the units of molarity as moles per liter, or I can express it as capital M, which represents molar. The concentration of a solution is often expressed in brackets, so if I want to represent the concentration of something, I simply surround that chemical symbol with brackets, and that symbol in chemistry means the concentration of something. Now, if we are trying to find the molarity of something where we know the number of grams of solute, the process is a little bit different because we have to first convert that mass into moles. The other thing that I notice in this problem is that our unit or our label for volume is in milliliters, so we also have to fix that before we actually calculate the molarity. The first thing that I need to do is I need to take 10 grams of lead-2 nitrate, and I have to use its molar mass to determine the number of moles of lead-2 nitrate that are in this solution, and that comes out to be 0.0302 moles of lead-2 nitrate. The other thing that I need to make sure that I correct before we actually solve for the molarity is the volume. And the volume is 200 milliliters, and if I simply convert that into liters, I get the final volume to be 0.2 liters. By taking the number of moles and dividing it by the number of liters of the entire solution, I get a final molarity of 0.151 molar. For this problem, I'm actually trying to solve for something different. I'm trying to solve for what the mass of the solute that I need is in order to create a certain concentration. So we almost have to work backwards for this problem. My first step becomes, well, laying out all of my givens and understanding that I have my volume, which I have to convert into liters first. I also have my molarity, and I can solve for my number of moles algebraically. My molarity equation is the concentration is equal to the number of moles divided by the volume. If I simply rearrange this equation, I get that the number of moles is equal to molarity times volume. Then I can simply substitute my numbers in. Since molarity is expressed in moles per liter, the liters are going to divide out in my final answer, giving me with the number of moles of HCl that are necessary. So the number of moles that are necessary are 5.76 moles. Then all I have to do is take my number of moles and use a one-step conversion to get it converted into grams. The molar mass of HCl is 36.46 grams. The final number of grams of HCl that are required would be approximately 210 grams of hydrochloric acid. I'd like you to pause the video and try these 3 practice problems. We'll go over the solutions here in a moment after you have a chance to work these problems out yourself. For problem number 1, we're solving for the molarity, so the first goal is we have to get our number of grams converted into moles. That comes out to be 0.00154 moles. And then I simply substitute that into my molarity equation. I also have to make sure that my volume is being expressed in liters and not milliliters. The final concentration should come out to be 0.0308 molar. For problem number 2, if we're solving for volume, the first thing I need to solve for is the number of moles of KOH that are in this solution. So by using the molar mass of KOH, I can calculate that the number of moles of KOH is equal to 0.00891 moles. By rearranging my molarity equation, volume is equal to the number of moles divided by the molarity. I substitute my numbers in. You can see that moles are going to divide out with moles, and 1 over liters is going to give me liters as the label for my answer. And then finally, to find the number of milliliters that are needed, I would have to take my number of liters and simply multiply that by 1,000 to get 89.1 milliliters. Finally, with number 3, we're calculating or we're determining how many kilograms of KOH or CaOH2 would be needed to use to make this batch. And the very first thing that I need to solve for is, well, how many moles are going to be required? By rearranging my molarity equation, I can solve for the number of moles. I know that I want my final concentration to be 1.5 molar. I know that I have 2.5 times 10 to the third liters that I'm trying to produce, and that's going to require 3,800 moles of calcium hydroxide in order to produce. Then I can use the molar mass of calcium hydroxide to get that into grams, and finally I can do a one-step conversion to get that converted into kilograms, so it will take approximately 280 kilograms in order to make this solution. Our next lesson will center primarily on how we handle dilution calculations as it pertains to molarity, but this wraps up our discussion of molarity.